So one more time, welcome back to COMP526, Efficient Algorithms. And we start another new unit. This is indeed my favorite unit, so I hope you like it too, because it combines a few things that we've seen before, and it has a few really remarkable solutions where when you see the problem first, you're inclined to believe that it's not possible to do it as fast as we'll see. But then along the way, each individual step towards that solution isn't really anything magic happening. It's just combining all those things together where suddenly you make this huge leap. We'll see an example where indeed a famous computer scientist also conjectured that something isn't possible, but he was proven wrong in the end. So it's on the one side, it's a cool puzzle where it seems there's no solution, but we'll see the solution indeed. It also is the unit where we get closest to the cutting edge research. Some of the algorithms are from this millennium, which maybe doesn't sound so recent, but much of the things, binary search trees, and some of the very basic things, these are among the oldest achievements of our field in computer science. Whereas here we're getting much closer to the state of the art. That's another reason why I like this module. It's also one where there's lots of research still going on. So what's this about? It's about text indexing, which is a way of saying we try to prepare a text to be searched quickly. And I put this subtitle of searching in genomes because that's one key application where this is used, but also is an example where some of the other simpler techniques just completely fall apart. We'll see more of that. The goal is for you to know some key methods for text indexing, and these are listed here. We'll cover them in detail. There's a specific data structure that is just useful to know, which is used inside of these in some sense. As always, I don't just want you to learn the algorithms by heart. I want you to know what the performance characteristics are, so that when you use them, where you usually won't implement them from scratch because they're standard methods, there's good libraries available, but you need to know how they behave to use them effectively. Same story as we had in many other units. And then going a little bit beyond what's already there, I want you to be able to combine things in a simple way, at least. Solve new problems using similar techniques, combining things from what we will see in this unit. It's a fairly long unit, but we'll go through it step by step. And we'll start today with some background on these mysterious tries that I asked you on Slido before the start. And then we'll also see the main star of the unit, the suffix trees. Let's first set the scene a little bit where we are and why we do this unit. The problem that we focus on is called text indexing, and it's basically the same as string matching that we've seen in Unit 4. But in this case, there's an important distinction, namely we call it offline string matching, because the text is static, it doesn't change. So it's similar as in Unit 4. We have a pattern that we're trying to find in the text, but the text is fixed and given to us in advance. So we're allowed to pre-process the text, spend substantial time there. At least reading the text might take a long time. Think of this as being a really long text. Whereas then we're given the queries for patterns one after the other, and we expect to answer many such queries. So it's well spent time to pre-process the text thoroughly and then be fast on the queries. That's the idea. It's from the terminology, we can say this is more of a data structuring problem than an algorithm. We're not looking for one single procedure. We're looking for also a way to remember something from this pre-processing. So we'll build what's called an index of the text. Well, that's Latin for one who points out. Your index finger comes from the same root. I'll talk a bit more about this in a second. There's many application areas that use indices in one way or another. The most prominent, I guess, are web search engines, while they're still around and not replaced by large language models. But even if they might be, we'll still have search engines in the classic sense because they're so much faster and cheaper. Online dictionaries in the classic sense of a word dictionary. So you're trying to look up a word. There you also don't want to start reading the plain text of all the words in your dictionary from scratch from the beginning whenever you search something. And then all kinds of other search functionalities on websites. I'll point out these genomic kinds of data types or text types. We'll come back to those. You can generalize it to also not just a single text, but text documents. And that's essentially these NoSQL databases use that kind of data model. So document-oriented databases. They usually also allow you to search, and they build an index in a similar way. The first way to do this, and a standard way that would be implemented in this last example, if you use a document-oriented database like MongoDB, they all do something like this. They use an inverted index. So the idea that comes from books. A standard index in a book, if you remember what that is, that means there's a list of keywords at the end in alphabetic order. And it tells you where you find that keyword in the book. Now, these are usually done manually, and it's a kind of a craft or an art to make a good index. Which words do you include? You don't want it to be too long, but you also don't want to miss important things. So in books, this is usually done manually. There's one key assumption here, which becomes obvious if you look through an index. We only search for entire words. So the whole thing is hinging on this notion of breaking the text into words. And depending on the language or depending on the situation, that is often a useful assumption. So what does an inverted index specifically look like? Conceptually, you go through your text once. You collect all the words in the text by splitting the text around some white space characters or others. I'll ignore this more linguistic aspect of it, that usually you don't want to treat all grammatical variations of a word separately, but instead you want to stem them down to the word stem they come from. So avoid plurals, avoid other tenses, and so on. But we'll mostly ignore this step. So it could be as simple as take your text, split it by white space, and then build one large map from words to the list of occurrences, so the list of indices in the text where this word starts. That's exactly what we would have found in a textbook at the end in a manually made index, except that this is taking all the words. We don't care if they're important or not. We include and if we want, so it's complete list of words. Question becomes still, how do we do this? So going through the text and splitting it up at white space, that's easy. And programming languages might even have a function for that. But how do we maintain this mapping so that we can quickly find, if I give you a word and that you can look in the table, I'll tell you a suffix and you want to find that. How do we do that? And that's where this comes in. So if you haven't had a chance to vote on this, you can do now. But probably most people will have cast their vote. So the thing is called a try, pronounced like in, I try to be a good person. I'll comment on the etymology in a second as well. Well, I take it that the majority hasn't seen it, or if they've seen it, it's not quite fresh, so we should spend some time on it. But let me go back one step here. So the key question now for inverted indices is, how do we make this fast, especially the query time? But all that this really asks for is a standard symbol table, same as we had. So in a way, it's just a symbol table where the keys are strings. Other than that, the abstract data type is the same. We just need a mapping from strings to lists of indices. So in particular, we could use a binary search tree, and it would work okay-ish. It's not the fastest possible option, but it's at least way faster than searching through the text from scratch. I just want to mention this in case you wonder why we don't just stick with it. It's an option, but we can do better. And one way to do better is these tries. And the reason why they can do better is that they exploit that we have strings. The binary search trees would have to work with any kind of data, whereas we can now exploit that we have strings as keys. So the name is traced to come from retrieval. That's why it's spelled in this awkward way. But then tree is kind of taken already and would confuse the heck out of people. So instead we say try. I don't know if that's a smart move, but it kind of became the convention. And so once something is a convention, it's hard to change. I also don't have a really don't have a better suggestion, I think. So that's just what it is. But you should try to be able to recognize when someone says try what that could be. In essence, it's a dictionary or a symbol table where the keys are strings. As in the past, we'll mostly ignore the values when discussing the implementation of a symbol table. But you can handle it in the same way as we've done for binary search trees. And instead of doing comparisons between entire strings, we'll work on individual characters. So to make that clean and nice, we'll make an assumption about the set of keys that we store. You can work around this, but for this unit, it's not necessary. It's the most convenient way to do it anyways. And it's also not usually a problem. So we make the assumption that our set of strings is prefix free. So no string is a strict prefix of another one. We've seen this before. We've seen this when we discussed compression and wanted a prefix-free code. Right, Huffman codes, for example. And there I already mentioned the term code try. If you remember, we've had the term there, and I told you forget about it for now. We'll cover it later. This is now, so. And you'll understand in more detail why this prefix-free was the key thing to require. But there's two simple ways how you can enforce a set of strings to be prefix-free, even if it wasn't from the start. Either if the strings are all of the same length, then, well, nothing can be a strict prefix of another if they're all equally long. So they're either either identical or they differ at some character. The other option is we append this end of string marker, and we'll use this dollar again. Again, something you've seen before in Unit 6. Just an arbitrary convention. But when you append this character to all the strings, you ensure that there's no prefix that occurs anywhere earlier. So here's an example of what this try looks like. And the way you should imagine using this is reading a path down to one of the leaves and then just appending all the symbols you find along the way. If you do that here, you find B, A, dollar, and that's what's written down in the leaf. And that's in general the construction. We have internal nodes, for example, the root, and they have children which are labeled by characters. So it's not like in binary search trees, left is smaller, right is larger, nothing like that. It's just all the characters in the alphabet can occur on these child labels, child edges. And the leaves store the entire string, which is a little redundant, but it's convenient for at least for drawing them here. So you can build such a trie by essentially, let me illustrate this with a smaller example with these two. So if I want to try for just a dollar, it would just be one long chain of things like this. A dollar. If I take the other one with 3 A's and then the dollar, these would be individual tries for just a single string. And if you want to get the trie for both of them, then you fuse them as long as they share paths. So these two are the root. Then they both go down with an edge labeled A. So we fuse these two into one node. Then we fuse these two into one node because they also are reached by the same edge label. But then things branch off. The one on the left goes down with dollar, and this one continues with A. So if I just wanted a trie for these two strings, it looks like this. You have 2 times an edge with A. Then you have the edge with dollar for a dollar. And you have another A. And then the dollar for triple A dollar. No credit rankings. Okay. So a few observations is it doesn't matter in what order you insert things. The structure of the trie is predetermined just by the set of strings that you store. That's unlike for binary search trees. Remember, we always needed to talk about inserting things in a good order. Question? Oh, I forgot the B. Okay, so this example is just for 2 different strings. So if you had a B, then there would be another edge. But I'm running out of space on the slide, so let's leave it with the smaller example here. Yeah, anything else? Right, so how do you search in a trie? The operations on a trie would be as in a symbol table. So you can, for example, check, is a given string part of the set that we store? And if it is, then you can store a value associated with it. And so to find a string, let's do this example with a dollar. And what you do is you start at the root and you traverse down the string by reading one character after the other. First, we want to see an A. That's fine. We can go with an A to here. Then we find another A in our query string. So we have to again take the edge with A. We find another A, so we go down here. Now our query string is finished, so we would want to see a dollar, the end of string symbol, but here there's no dollar. So that would be the point where we can conclude that string a dollar is not part of the set of strings that this trie represents. Whereas if you ended up in a leaf, then you would have found that string and you can look up what value is associated with it. Let's also do an insertion just to show that to show how this looks in a larger example. Let's insert a short string BA dollar. So as always, almost always, you start by searching for this thing. So we start at the root, then we read the B, so we traverse in that direction. Then we read an A, but there is no A at this point. So we just add another child here with the new label A. And then, of course, we don't have this node before, so we also need to add the next edge. And we append a new leaf. Let me draw these a bit straighter. Okay. That's how you insert things. And you should think of course, all those lines are represented as pointers in some object. And so adding a new line is essentially setting a pointer to a new object that you allocate. Let's see if that has sunk in a bit. So specific concrete suggestion as situation, we have the standard English alphabet or Latin alphabet. We have n strings overall, and they're equally long, so we don't even have to worry about end of string characters. But now the question is, how long does a query take? So you're querying with a string q, which is potentially shorter than m. And the question is, how many nodes in the trie are visited? Okay. I'm not allowed to make it smaller to fit all the answers on the screen. So we've had around 110 for the last question. So I wanna give you a second. Maybe let me go back to the example picture. It seems most people are done. So let me show you the votes. And again, they don't all fit, but almost. And so the right answer is this one, as many of you found. Here's a bit cleaner to see. Why is it Q? You have to visit as many nodes as there are characters in the query, and that's pretty much it. Sometimes you're lucky that you can stop early. And the example is set up so that you usually don't, you can't usually stop early. I guess So I guess it asks about the worst case, and in that case, you cannot stop early. But the important bit here that I want to stress is the running time is only depending on the pattern. The length of the pattern that you search determines how long it takes. It's completely irrelevant how many strings there are and how long they are, right? And in a way, that's remarkable, because you would assume you have to somehow read them all, or at least pay some log n cost or something. But no, it's nothing like that. If you look for a short pattern, you pay exactly just this cost q, which will be very cheap if q is reasonably small. But let me ask a second question. It's essentially the same situation, but the question now is asking for a different thing. It's asking about the overall number of nodes in this tree. So the question asks about these red blobs that I've drawn in this example. Let's wait till 60, but I see there's some somewhat reasonable agreement on an answer. In case it matters, you can assume that n and m are fairly big. So it's an asymptotic result that I'm looking for. So here are the votes, and indeed the majority vote is correct. Let me briefly explain why that's the case. Well, what happens in a worst case is that essentially all the strings differ very early on, as early as they possibly can. So the trie would look like this. You have a fan out of 26 for each of the possible letters. I'm not going to draw this in its entirety. And then each of those can again fan out 26-fold. Up until a point, so you need to go down this for log base 26 of m levels. Then all the strings can be unique. And from them on, you just continue with long chains of nodes that end in a single leaf. Okay? So you do this all the way through. So that second part, it looks in the picture like this is almost equally tall, but it's if you make m big enough, then that's essentially m minus this. And this log m, log base 26 of m, if m becomes big, that's a vanishing fraction. So most of the all of the n strings, that's the other dimension I could draw. So the number of strings that you have here is n, or n leaves in the end. Each of these n strings contributes m minus a tiny bit of nodes that it doesn't share with any other string. So if you just look at this rectangular part at the bottom, these tentacles, they contribute essentially, asymptotically, they contribute n times m nodes. And that's where this worst case comes from. So what does that mean? Is that good or bad? That depends a bit, but it kind of is annoying. In one way, it's not as bad as it could be, because n times m, that's the total length of all the strings. And arguably, we have to store the strings. So maybe it's inevitable to pay that space in this case. On the other hand, it feels very wasteful, especially this worst case. Why do we have all these long chains? They seem to be wasting space, and they also seem useless from a search perspective. As soon as you're on this long track, you kind of know there's only one string that will be the match, or it's not the match, but there's only these two options. Okay? So overall, in the general case, you may not be able to avoid space similar to that, but we're not quite happy because it seems to leave potential on the table. And the answer to that is called a compact trie. It's a very, very simple little trick that just gets rid of these long tentacles at the end. Whenever you have in a trie a path where one node has just a single child, you get rid of that node, you eat it into the parent. So here's the example from before, which was well, we call it standard trie to distinguish them. And it has a bunch of these parts where it has unary nodes, for example, this one. And so what you do is you contract that into this edge. So that becomes just this one edge. I'll talk about the labels on the edge in a second, but let's do another example here. So it could be one of these long branches down to a leaf. These we also compact down to a single edge here. And you do this all the way in the trie. So whenever you have a node that has a single child, you can contract it into a single edge. Now, that loses some information. We lost, for example, this character b here. There's a single b on this edge. We can't really throw away that information. But in this case, we still have the entire strings at the leaves anyways, so we don't really lose the information. It's stored somewhere else. But we lose something else when you think about searching the trie. Suppose we're trying to find whether BA is in the trie. Okay? It's the same example that we inserted earlier. So if I do this in the standard trie, I move down to B. And then, oh, there's no A, so fine, it's already over the game. I know BA is not in the trie. If I do this in the compact trie, I find the B. I miss that the second part of this edge should be a B. And I might conclude, oh, maybe I have BA. In this case, there's no way to continue with dollars, so let me modify my example to BAB. And then the dollar. So same story here, B, and then I already fall out of the tree, so I know it's not in there. If I do it here, B, and then it continues with the B at this later position, I'm skipping one character. I might mistakenly think it's this guy. And second problem, I need to know which character I'm comparing. So that's why in the compact trie, the internal nodes have these numbers, which tell you what is the index in the query string you're looking at. We didn't need that here because we always went down one edge, and we knew we always go to the next index, always +1. But here, because we have these contracted edges, we might jump over some characters. So that's the two caveats that they need to take into account in compact tries. Because we're contracting edges, we need to remember which index are we comparing next. And we need to keep in mind that we're throwing away some information on the edges if we're doing it like this. It's more extreme on this case even, where we just keep the first A. and then all the remaining characters are just stored in the leaf. So that makes the searching in the compact trie a little trickier, but not overly more complicated. Let me do the example here properly again with the explanation. We start at the root, and we have the indices of the characters. We start at the root, we look into the root and ask what character are we supposed to compare next. In this case, it's character 0, so we look at the B. So the next edge down from there is determined by whatever that first character is, in this case B. So we go from here down to that one. Now that node tells us index 2 is to be looked at next, so we just look at this, and we go down here. In that case, we find a leaf, and then we still have to do a last check where we compare the entire query string to the string in the leaf. And in this case, we would find that BAB is not the same as BBB. So we would have to declare the key is not contained in the symbol table in this case. But that's how the search works. So this slightly trickier is just these two things. You have to check the index you're comparing, and you have to compare the entire string at the end, because it might be that you jumped over some of the characters. What we get from this is that all internal nodes have at least 2 children, because the ones with a single child we got rid of. What does that mean? Well, that's a classic little argument of counting in a tree. The number of nodes is at most the number of leaves, because with every internal node, if you think of starting with n leaves, these are n little slots that we somehow have to connect into the root at the end. And every internal node at least takes 2 leaves and has 1 parent pointer going up. So I think of it as this. If you have 4 leaves, they all stick a thing to the top, and we have to somehow put something to this half pointer. If I take any internal node, it has at least 2 slots going down and produces 1 up. So at least it goes down by 1. And that's true for every internal node. And it's even better if they have higher degree, than they eat more than 1. But always we get this inequality. The number of internal nodes in the tree is at most the number of leaves. The number of leaves is the number of strings. So we get that the number of internal nodes is linear in the number of strings. So we get space n instead of n times m for the trie. We still have to store the leaves. We'll worry about that later. But the number of nodes is linear. So linear in the sense of order n in the previous notation. Let me also briefly comment on what we have to store for each internal node. We have to store a number for the index. That's fine. That's a single word. And we may have to store all the outgoing edges. But we're assuming that the alphabet is fixed and small. So we can just list those all, and it remains linear. But technically, for storing the child pointers, we get a contribution of n times sigma overall, where sigma is the size of the alphabet, because I might have that many child edges for each node. You can try to be clever on that, but for the general overview, that's enough. That's pretty much what you need to know about tries. There's 2 versions, the standard and the compact one. We'll often think in terms of the standard trie for the algorithms, but what we really want to store is the compact trie, because it's more space efficient. And you can use tries as they are, as I've shown them, as an inverted index, and they would perform reasonably well. As long as this fits in main memory, that's pretty fast. And they're arguably quite simple compared to other options. And the lookup is as fast as you can get, because it's just depending on the query length and no other contribution. Even if your index is the Google search index, the entire web, the search query might only have to look at as many nodes as there are symbols in your query string, and that's super small. This simplicity comes at the price that it can't do some other general things. If you want to search for just a part of a word, that's just not supported. From the get-go, we said split the text into words. So we can't do that. For search engines, you would also want to search for phrases of several words. And that's not clear how to do that easily or efficiently with the try in that way that we presented it so far. But we'll focus on the first problem, that for some texts, there is no such thing as a word boundary to start with. And so the whole process of the whole idea of using an inverted index seems to break down. And two examples would be biological sequences. So your genome, your genomic sequence, the DNA sequence looks, I mean, this one, I think I made it up, but it looks something like this. And if you have a binary file, you might also want to search for patterns like essentially a virus scanner would do. And there's no words in there either. So for that, it seems we need entirely new ideas.